Hello everyone, and welcome to this webinar on supporting the design and achieving requirements for sustainable urban drainage systems, or otherwise known as SuDs. The drive towards SuDs as a preferable alternative to traditional drainage types is becoming ever more popular with asset owners, both in the private and public sectors. Globally, extreme events that cause increased flood risk are becoming the norm and at an escalating frequency. So we must ensure that we are designing for both the current situation and achieve climate resilience by ensuring our system is suitable for the future. In this session, we're going to look at why we need to transition to SuDs and the technological solutions that help support the design process. My name is Jonathan Brookfield, and I'm a technical consultant here at Diatec Group, situated in the UK, but covering both the UK and Ireland. My industry background is primarily based at engineering consultancies, including experience with contractors, having worked for a cohabiting joint venture. The sectors I have worked in have predominantly involved water, so having delivered projects for maritime ports and harbours, flood alleviation and coastal defence schemes in the UK, in Europe, the Middle East, Africa and South America. I possess qualifications and certifications and charterships in civil engineering, building information modelling or BIM, and virtual design and construction or VDC. As a technical consultant, my role is to help our customers achieve their organizational goals through digital transformation, demonstrating and realizing value by looking at production management or process, change management, software implementation, and training and upskilling. So just a little bit about Diatec Group themselves. So established in 1984 with over 50 staff in the UK and Ireland, Diatec Group is a leading technology partner in the AEC sector. We are an Autodesk Platinum partner and accredited training and certification centre. In 2023, we recently became part of the NTI Group. This means that we are now the biggest EMEA Autodesk Platinum partner, which so we have extensive access and support from Autodesk and their experts. NTI holds all Platinum Partner certifications within the architecture, engineering, and construction space, the design and manufacturing, and media and entertainment, with all the other underlying certifications that go along with those. We are also a part of the Sustainability Tech Partner Programme, where we are close to all the new development and align with Autodesk on this. Very large international AEC team, which means we can also possess our own IP with a professional development team. This also means that we are part of a big group with experts that can be relied upon when needed. We can support companies across borders. So if you have subsidiaries in other countries or other regions, you can rely upon a single or the same partner across all of those. The topics we're going to cover today include an overview of SuDs. So what are they? What are the benefits gained? How does this affect and disrupt the design process? Once we've established the general principle of SuDs, I'm then going to take you through the design of typical SuD structures and how we can harness more sophisticated technology to aid in this process. As the webinar has sustainability at the forefront, we're going to look at pollution in drainage design. What types of pollutants are we looking for? What are their impacts? How can we model them? And how can we mitigate against pollution in drainage systems? With change comes a level of disruption, but this disruption isn't always negative. With alternative drainage design principles comes a requirement on how we achieve this new criteria. So we're going to look at tools that can help us effectively communicate, collaborate, and transfer data. As our final topic, we're going to briefly touch on outputs and reports relating to SuDs design and how this can be achieved to meet local and regional drainage requirements. We'll then finish off the session with a Q&A session. So just looking at what SuDs actually are. So SuDs design is about looking at how surface water is managed in a sustainable approach, more so than traditional gully and manhole systems or traditional conveyance systems. As precipitation events occur where the water lands on natural landscapes, it soaks into the ground, a process known as infiltration. Water on the surface will also be removed from the surface via evaporation. It can also be taken up by flora, fauna, and trees in a process known as evapotranspiration, and some will find its way into watercourses such as streams, rivers, and lakes. Where the natural water cycle is hindered is when the landscape has been disrupted by man-made development. When we look at heavily developed urban areas, we know that there is far less permeable ground for infiltration to happen than in, let's say, rural or countryside locations. When rain lands on impermeable surfaces such as asphalt and concrete, a higher percentage of this turns into water runoff, which can lead to flooding, erosion, and pollution. It's a common misconception that because a structure is situated far from a watercourse, so something such as a house or an office building, that it is not susceptible to flooding. Surface water or pluvial flooding occurs when extreme storm events happen, exceeding the capacity of the existing drainage system, combined with a large percentage of impermeable surfacing in that location or area. Delivering resilience is imperative. We must be able to adopt solutions that not only look at the here and now, but can also cope with future changes in our climate, such as more frequent critical storm events. There are more benefits to SuDs, though, than just the SuDs implementation, than simply the control and removal of surface water. So, by introducing SuDs, an area's biodiversity is likely to improve. This is due to the increase in vegetation use, such as well as the variety of fauna and flora that is implemented. So, for example, a green roof is likely to use grasses or alpines requiring small amounts of soil and are pretty much drought tolerant, so things like sedums. Retention ponds encourage aquatic life, planting, and birds. Bioretention strips can consist of wild flowers and shrubs, encouraging insects and other pollinators. Where vegetation is introduced, particularly aspects such as the planting of trees, this will contribute to our fight against climate change, particularly in urban areas. So, an increase in tree planting allows for carbon capture due to the trees soaking up CO2 from our atmosphere. Sod structures also require less embodied carbon as they mitigate against materials such as concrete and plastics. Due to the infiltration properties of sod structures, the water released has been pre-filtered, thus reducing solid pollutants, improving water quality. One thing I believe we learnt from the COVID pandemic is the importance in urban green space, particularly in denser populated cities. So SuDs provide beautification, or at least help support beautification as aspects such as parks, flower beds, and water features. Introducing well-managed natural and green spaces improves the quality of life and desirability of zones and areas, making it a better place to live and work. So, thus having a positive social and economic implications. Introducing more areas of filtration and less use of non-porous areas such as roads and pavements allows for a reduction in flooding, particularly during flash flood precipitation events. By using the existing natural environment alongside a range of SuDS techniques, we're creating a more effective drainage system using less materials, less hydrocarbons with less maintenance. So essentially thus doing more from less. And finally, we have rainwater demand and reuse. So we've all seen or may even own water butts for collecting rainwater to be distributed about the garden. What this notion is effectively saying is it's the same thing, but on a grander scale. So what we can start looking at is the rainwater harvesting of, let's say, a house by having a water tank that sits beneath something like a driveway, where we can reuse this water for aspects such as car washing, watering the garden, or even using it in washing machines for clothes. This water is traditionally known as grey water, but by reusing it closer to the source, we are reusing it in a more sustainable manner, especially when we looked at the amount of drought conditions that we're seeing in recent years. So we've discussed the high-level benefits of SuDs features, but what are the principles specific to designers? Here we have the four pillars of SuDs design as described in the UK DEFRA Syria manual. Sorry, Syria SuDs manual. To satisfy requirements, SuDs feature design must adhere to these four sets of criteria as a minimum. So when approaching drainage design, we must consider water quantity, water quality, amenity, and biodiversity. We won't run through all of these points listed. However, to highlight a few, when looking at water quantity, for example, one of the items we need to design for is ensuring we protect the formation and shape or morphology of receiving surface waters. For taking water quality into consideration, we need to ensure that receiving waters and groundwaters are managed, looking at aspects such as pollution prevention by implementing systems for interception and treatment. When looking at amenity, we need to deliver a safe surface water management system, so developing things like health and safety risk assessments, for example. It is important to point out here that SuDs structures are no more hazardous than natural ponds and wetlands, puddles and surface runoff flows on roads, or in streams and rivers. Where we have deeper waters and steep slopes, we need to consider the implementation of edge designs, safe slopes and barriers. Finally, we have designing for biodiversity, where we need to look at items such as creating a diverse, self-sustaining and resilient ecosystem. This means that not only will it need to flourish and survive in the current scenario, it must be resilient to future climate changes such as extreme rain events and drought conditions. You may actually interact with SuDs on a daily basis and not even realize it. So for those less au fait with SuDs design and structures, to put it into some more context as to what we are talking about, when we refer to SuDs, here we have a few common examples. Swales are a shallow channel with a gentle side slope in the ground, where water running off a site can collect and soak away. They are commonly found alongside roads, pavements, and car parks, allowing surface water to run off and infiltrate into the natural sublayers. They are also a form of conveyance, which means they move water and can move and slow water during heavy precipitation. Retention ponds are artificial lakes used to store surface water and other types of runoff. They are permanent features like a reservoir and help to store water local to the source. Detention basins are usually a dry and a feature of using a grass surface, providing an area for infiltration to occur during precipitation. They also help to filter out pollutants from road surface runoff. They commonly double up as green space and are often found next to children's play areas in urban environments. Green roofs consist of vegetation planted over a waterproof membrane. They absorb water, provide insulation, and create a habitat for wildlife. Permeable paving solutions are either made of a porous material or spaces are left between non-porous units, allowing water to flow between the gaps, like the image shown. So what we've got there, for example, is interlocking concrete blocks with a gravel joint between them, so water can filter on through to the sublayers below. So finally, we then have bioretention strips that are shallow landscape depressions, pretty similar to swales, which also consist of engineered soils, enhanced vegetation, and filtration. So, like swales, they are commonly found adjacent to hard landscaping such as roads and pavements. So, what is the technology that we would look at implementing for designing for sustainable urban drainage systems? So, info drainage is the next generation of drainage software, replacing the ever popular micro drainage. It was built with sustainable urban drainage systems in mind and allows us to develop designs and analyze models more realistically than ever before. Also, we can meet a variance of regulatory requirements by customizable output report templates to help ensure environmental protection, support community resilience, improve the productivity of design teams, reduce errors and rework on projects, and save time and costs for all stakeholders. Like previously mentioned, InfoDrainage was built with SuDs in mind. This means that we can design true to site structures with accurate footprints, including correctly positioned inlet and outlets. Each stormwater controller has its own unique set of parameters, properties, and calculators to help support the user. Here we can see the design for a retention pond specifying the outlets. Not only can we accurately locate where the water is going to flow out of the structure, we can specify the outlet type, be it a weir, flap valve, orifice, or pump. Furthermore, depending on the outlet type, we have a series of options specific to the control, to that control. So, for example, a pump is going to have a different set of parameters and calculations when compared to a gate. Here we have the properties menu for porous or permeable paving. Under the Dimensions tab, you can see we can control and specify the exceedance elevation, overall depth of the structure, the base elevation, paving layer depth, or height of the paving blocks, membrane percolation, porosity, length and width of the structure, and any gradient and slope that needs to be designed for. Furthermore, we're able to automatically extract data present in the model. So, for example, the base elevation can be automatically taken from a tin surface present in the model that has originated from software such as Autodesk Civil 3D. And as our final example, to give you a flavor of the breadth of properties we can define within the software, here we have the filtration layers for a bioretention strip. Here we can define the types of materials used, the depths of each layer, and the characteristics relating to the materials, such as the porosity and conductivity. These are manually inputted, however, we are provided with a useful calculator to determine the soil type properties, so such things like the field capacity and the wilting point. Moving on from designing substructures, let's take a look at analysing pollution inside drainage systems using info drainage. So here we have a general list of pollutants that we may need to mitigate against in drainage design, depending on the type and land use. So for example, we have a list of pollutants that originate through atmospheric deposition. So this is a process whereby rain, snow, fog, particles, aerosols, and gases transition from the Earth's atmosphere onto the surface terrain. So if our asset is a road or rail infrastructure project, we're going to have to consider the various pollutants caused by vehicles. It could also be leaks and spillages, and de-icing activities such as the gritting of roads during winter conditions. Where our site is in a more rural setting, we'd need to consider aspects such as animal feces, vegetation and landscape maintenance, and the effects from soil erosion. Regulatory requirements may dictate that we need to demonstrate the percentage removal of pollutants from the site being analysed. Inside Autodesk Info Drainage, we have a few ways we can assess and design for pollutants. We need to begin by scheduling what pollutants we need to mitigate against and which ones are likely to be present on our site. This may vary depending on whether the site or the asset type is a road or car park, residential estate, industrial complex, and so on. These pollutants will be like the types of pollutants we looked at on the previous slide. We can do this inside the software by using the pollutants menu under the rainfall pollutants tab on the ribbon and entering each pollutant item that we would like to analyze across the site. You can see in the example that we have listed two pollutants, so total suspended solids and total phosphorus. This schedule will then be harnessed elsewhere inside the software, depending on the structure types implemented. We can, of course, analyze far more than this. It is up to the user or defined by the regulatory requirements as to what we need to assess. Once we have scheduled our pollutants, we're able to define where on the site these pollutants originate from and the concentration in milligrams per litre. So just as a bit of a side note here, if the location we're working in stipulates that we need to present this data differently, so for example, we wanted the concentration to be supplied as fluid ounces or gallons. We can change this due to the flexibility info drainage possesses when approaching regionalization. We can see from the example we've applied two pollutants to an inflow or catchment area and specified a concentration for each. Beyond stipulating the concentration of pollutants in our inflows, we can assess how substructures deal with the pollutants as the water runs through the structure. As you can see, we can identify how this is analysed via the structure properties. In this case, we have an infiltration trench. Here we can decide upon how the pollutant concentration is calculated, either by first order decay or percentage removal. When we want to calculate our first order decay methods, we have a useful calculator working on residence time to help fill out some of the inputted parameter requirements. We'll find throughout info drainage that we have lots of useful calculators to help us input data to help reinforce our outputs. So with the 60-minute half-life that we've inputted, we'll be able to analyze how long the pollutants reduce over time, depending on how long the water remains in the structure. So this is particularly useful if we were to look at a retention pond or a swale. When we perform the analysis on our model, we can assess the concentration of pollution changes during a storm event. We can then mitigate against this by adding further structures such as detention basins and swales to help further reduce the concentration of pollutants on the outputted runoff. As we can see, we can toggle on or off the pollutants graph when assessing the results of a stormwater control structure. This will help us demonstrate compliance when submitting to local drainage authorities. Okay, so moving on from designing for pollutants, we're going to look at workflows and collaboration. When we look at a traditional approach to drainage design, due to the impact it has on project timelines, it would need to be frozen as soon as possible alongside the finished paving levels. This could lead, or usually did lead actually, to overly conservative, unsustainable designs due to the drainage design being on the critical path. So with the introduction of things like digital transformation and building information modeling or BIM principles, there is a shift in the data that we can expect from the design teams that we wouldn't have ordinarily asked for in more traditional projects. This combined with more emphasis towards sustainable construction and operation of assets means we have to do things differently. With sustainability at the forefront, More key performance indicators or KPIs are going to lean towards aspects such as embodied carbon and other types of carbon calculators. So, thinking more about the sourcing of local resources and reduction in material transportation costs. Understanding our process is important to adapting to new design environments. Traditionally, we'd have seen more of a sequential or dependent workflow where the drainage design would have to wait for the civil design or vice versa. This means if changes, iterations, or refinement is required, teams are put on hold to wait for updated data to filter through. Ideally, we'd want more of a reciprocal or interdependent workflow where teams can translate, share, and progress data in parallel. To accommodate for this, we need to have the right tools at our disposal. With the use of Autodesk Info Drainage in Civil 3D, we can perform a more reciprocal workflow between the civil and drainage designers. The first key feature I'd like to highlight can utilize is that Info Drainage can utilize DWG files for background layouts, and it can also utilize tin surfaces created inside of Civil 3D. When an analysis file is created by Info Drainage, it produces a .iddx file, which this same file can be opened inside of Civil 3D in the form of a pipe network for the traditional drainage aspects, such as the structures and pipes, and feature lines with surfaces representing the substructures. Both applications can host their files inside the Autodesk Construction Cloud, so via the use of Autodesk Docs. So this allows us for any remote working and efficient accessibility for data. We discussed the notion of doing more with less when looking at the benefits of SuDs, and I think a reciprocal workflow is required to achieve this. We also talked about protecting the morphology of receiving watercourses and surface waters when looking at the four pillars of the SuDs design. I think this can also be applied to the general terrain or topography of the site where possible. So, for example, if the drainage design influences the site earthworks design, utilizing the existing terrain as much as possible, it results in less disruption to the natural landscape and reduces the need to deliver more excess material to and from the site. So, to output the most effective and sustainable design, we need to perform a level of optioneering. We can enable this inside of Info Drainage by using the phase management tools. Phase management allows us to have multiple designs in parallel to develop the most sustainable system to meet all of the criteria. So, for example, we have run our analysis and found we still have too high a concentration of a pollutant at our retention pond. So prior to the water being released into either a receiving watercourse or an existing drainage network. We can keep this proposal intact and simply duplicate the phase. In our new phase, we can introduce a form of infiltration to reduce and capture more of the pollutants upstream. So by doing this, we have kept both of the designs, but what the application then allows us to do is compare the analysis between the two proposals. So this provides us with evidence as to why we need to introduce a further substructure if costings are ever questioned and so on. In our final section, we're going to look at some examples of products and outputs that we can export to aid and support design teams in creating their deliverables. So, depending on who the stakeholder is, there is going to be a variance in the outputted products. So, for example, if we were delivering information for for regulatory approval, we'd need products such as calculations, reports, and drawings. If we're focusing on delivering construction information, we'd need drawings, models, schedules, and bills of quantities. And if we're performing public engagement and consultation activities, we'd need items such as an impact summary and a visualization of the proposed scheme. So firstly, let's talk about simulations. We can provide simulations in plan, profile, and 3D views. So this is useful for all types of stakeholders to understand how the system works. Of course, simulations are always extremely beneficial when delivering information to non-technical stakeholders, especially when you are doing things like public consultation. With this, we can also provide profiles along drainage and flow runs to establish what happens during a storm event, the relationship between the terrain and the structures, and the positioning of items. We can also record our simulations on a profile as a video, or we can output them as static PDFs for use within other documentation. When gaining regulatory approval, reporting is imperative. We can report on almost all the data found inside of info drainage, depending on the intention for that document. So for the report to be accepted by various regional authorities, we need to be able to deliver specific criteria. What info drainage allows us to do is just that by selecting the exact data required for that specific local body. For efficiency and repeat clients, these reports can be templated, so users don't have to run through the same selection process each time they create a model and want to output the report. For supporting technical outputs, info drainage has various ways of extracting key data. So if, for example, a user needed the layout inside a CAD application, we can export the plan to a DWG format. We can also have a seamless bi-directional connectivity with Autodesk Civil 3D that we looked at before. For GIS users, we can export the data for use inside applications such as Esri ArcGIS. And where raw data is required, we can export the drainage system to Microsoft Excel or Land XML. I appreciate we've covered quite a lot in a small space of time there, but hopefully what you've seen today gives you a flavour as to why we should and actually need to transition to more sustainable drainage alternatives, and actually how the technology has been developed and adapted to support these types of systems or structures. So I suppose from me, thank you very much for your attendance, and I hope you enjoy the rest of the NTI Sustainability Summit. We're now going to close this presentation, but we're then going to go into a brief Q&A session.
Hi all. Thank you very much, Jonathan, for that excellent presentation. We have time now for some questions relating to SuDs. The Q&A box is open, so please type in any questions you have. If you would like to contact Diatec for anything related to Autodesk training, software, related hardware, and digital transformation, you can find us at diatec.ie or contact@diatec.ie. Diatec are now, as of November, part of the NTI group, and Diatec are trusted digital transformation partners for some of the biggest names in AEC in the UK and Ireland, and we'd love to hear from you. So we do have some questions here that I'll pitch to Jonathan. The first one is, what region does info drainage currently cover?
Yeah, okay, so the way info drainage works is it's a single application. So essentially at the moment in time, there are some presets that come out the box which will adhere to particular local and regional governing bodies. So those at the minute, if I can remember, are Australia, China, France, the UK and Ireland, the US, and then there's a global setting which can adhere to all of those situations. So if you need if, for example, one of those regions is where isn't where you reside, you can still use the software platform. It just depends on actually what kinds of calculations you need to output. What regionalization actually includes is a series of things such as rainfall data. It's auto sizing for things like preliminary pipe sizing calculations and different types of runoff methods. So how those are calculated in a particular locality. But just to reiterate, you can still use this no matter where you are. It's just at the minute, what in Autodesk have provided you are a limited series of presets at this moment in time.
Okay, thanks, Jonathan. And thanks also, Elena, for that link to the Diatech website with more information on inner lines and info drainage. That is there in the Q&A. Second question, when exporting to Autodesk Civil 3D, how does Civil 3D handle the SuDs structures?
Sure. So those of you who are more familiar with Civil 3D, using it with perhaps things like micro drainage in the past, or using the SSA, so the storm and sanitary analysis software that used to be inside of Civil 3D. Basically, the what info drainage does is when it connects to Civil 3D, traditional elements such as pipes and structures stay as is. What changes is actually things like, we've now included things like retention ponds, swales, and bioretention strips, for example. How they come into Civil 3D is as feature lines and surfaces so that you can manipulate them. They must start their life in info drainage, but what we can do is we can manipulate the sizes inside of Civil 3D. So, for example, if we've developed and analyzed a pond structure inside of info drainage, once we bring it into our Civil 3D model, that might clash with existing utilities. It might get in the way of other pieces of structural design work. So what we can then do is manipulate the size of these structures inside of Civil 3D to then return it back to info drainage to then reanalyze it to ensure that it still meets the drainage analysis criteria, as well as doing the design coordination inside of our geometrical software.
Thanks, Jonathan. You also talked about various stormwater control structures, in particular retention ponds. What other water retention structures are available?
Yeah, so we looked at retention ponds just as a primary example because we had a very limited time on what we could actually cover in the session. But as different storage types and applications that we can use, we can do things such as cellular storage. So when we're looking at crates that we see under the ground, that we can start utilizing those. We can also look at chambers, so different multiple water chambers that sit beneath the Earth's surface. And we can also look at water tanks, so a single water tank that's going to be used for storage. I mean, we touched on this with rainwater harvesting in the presentation as one of those benefits of SuD structures. So what we can look at inside of info drainage is actually, if we are doing, let's say, a housing development, we can implement storage tanks to go with each house or area to then store that water local to the source to be reused in things like watering of gardens and grey water use, so washing cars, things like that.
Okay, and are we able to assess the system when it is exceeded?
Okay, so we're talking about kind of flooding essentially here. So when we look at design criteria for drainage systems, we generally look at it in an assessment that we need to think about this logically, that actually this drainage system might flood. What is a worst case scenario, and what actually happens when a surcharging does happen, so water comes up through our structures and floods across surfaces. So what we have inside of info drainage to take into account this is a 1D and 2D analysis, which allows us to see in a most severe storm event what happens. So where does the flooding occur first? So which structures in our system are affected, but also what then happens to that water once it's gone through and out of a manhole or out of a gully. Where does that water then travel to, and where does it pool and collect? So we can use both the surface data and our system to assess that. But we can visualize this both in plan, we can visualize it in sections and profiles, but we can also have a 3D output of this. So as the storm event happens, we can see where the water's rising and then where that water is moving to.
Okay, thanks. And we saw the ability to include catchments when you were talking about pollutants. What other inflows are available?
Yeah, so we briefly covered on catchments for the pollutants, so understanding where our water begins in our cycle. So beyond just looking at a rainfall catchment area, we can add in, if I think off the top, so we've got a base flow, which is basically just if we were attaching our drainage system to a existing system, we can just tell it by what flow of water is already coming into the system at that point. We can have catchment areas, of course. We have green roofs. So where we've added in a sustainable urban drainage system, we can start looking at, if we've got urban structures and we've added in green roofs, what is the infiltration of those? What is the flow rate of those inlets into our system, and so on. So green roofs is another. And finally, if we have the data available, we can add in hydrographs. So for things like water courses that are adjacent to our system. So what happens in a storm event? Where does that water go, and how does that contribute to our system? There is one thing that those of you who are more au fait with drainage systems might be thinking about is, we talked about permeable paving. So looking at how water flows into a permeable surface. Most people would consider that an inlet or an inflow as opposed to a stormwater control. But it's seen as both in the software, and it comes under a stormwater control as opposed to an inflow. So what we would need to consider if we do have permeable paving on our site is we need to put a catchment area over the same area where our permeable paving exists. So it takes into account the rainwater that is landing on that paving surface, as well as how that then is controlled by the pavement itself. So that's one thing we do need to consider when we are looking at substructures, in particular permeable structures in that. Hopefully that explains that.
I'm sure it does. Are there any other questions from the attendees before we close out the session? Give it another second.
If not, Theon, thank you everyone for your attendance. First off, it's a very critical subject, this actually, the implementation of SuDs. And what we're seeing with our customers at the moment, I mean, it was only last week I was supporting someone with their info drainage implementation, purely because SuDs is becoming more prevalent with places such as Ireland, for example, where
it is absolutely lashing out here in Dublin. So yeah,
yeah, places which get a lot of rain, but also need to look at. We're seeing higher levels and more critical floods at a higher frequency. And we've got something in the UK coming in this year, which is the Schedule 3 of the Flood and Water Management Act. And that's going to mandate more SuD structures are implemented on local authority drainage schemes. So I'm sure that's been echoed around Europe at this moment in time. So we're going to see it's going to be more of a hot topic.
Absolutely, absolutely. And it's great to see something that is not intrusive and generally can potentially be aesthetically pleasing as well when it comes to sustainable solutions for flooding, which often includes, concrete barriers and walls and that kind of thing. So and the added benefit of being good for wildlife and helping to achieve those biodiversity goals as well.
Sure.
Yep. Yep. Okay, I think that closes out the session, and Diatech would be very happy to hear from any of you if you have any further questions about sustainable urban drainage. But thank you very much, Jonathan, for your presentation, and thank you very much to all the attendees, and of course our NTI tech team who've been looking after us as well. So thanks everybody, and we'll hopefully chat again soon.